Okay, so, great. Today I'm going to talk about lens surgery and, well, not the classical lens surgery in three manifolds, but rather its group theoretic analog. And first of all, let me remind you what the classical geometric lens surgery is. So, lens surgery is the process of getting one three manifold from another three manifold. And roughly speaking, it consists of the following tricks. So first you start with the three manifold, you embed a knot in it, and remove a small neighborhood of that knot. That's called drilling. So you kind of drill along the knot. And then what you do this way, you just remove a solid torus from your manifold. Then you do the solid torus back. So to be more formal, so let's start with some manifold. Let's call it M, and for simplicity, let's assume it's closed. Although it's open. So then, what I do, I take a knot, say K, and embed it in my manifold. I don't know how to draw a knot, I'll try. Okay, that's my knot, which is probably an unknot. No, that's a real knot. Yes, but that's not the one which I want. So it's not a hyperbolic. I want a figure 8. Anyway, so now let's call this M. So M is M, which is my original manifold, minus some small neighborhood of the embedded knot. So what we get a manifold with boundary. So what is the boundary of this manifold? Well, that's two-dimensional torus, right? Well, that's denoted by S1 plus S1. Well, which is the same as the boundary of the solid torus. So the solid torus is what we remove. C2 for me is S1 cross this. So now we can fix a homeomorphism, let's call it phi, from the boundary of my manifold to the boundary of the solid torus. And then we just glue the solid torus to my manifold by using this homeomorphism. So what we get is M union the solid torus, where these two guys are glued along phi. So this is a new manifold. If the original manifold was closed, what we get is another closed manifold. What's good about this process, it's kind of an elementary transformation, in the sense that every connected orientable, let's say closed three manifold, can be obtained from the three-dimensional sphere by doing finitely many surgeries like this. Or just by doing one surgery if you allow links instead of nodes. So this is sort of elementary transformation. If you want to prove some theorem about three manifolds, all you have to do is to prove it for the three-dimensional sphere, and then to check that the property you care about is preserved by this surgery. Of course, it almost never works, but still so it's hard to check that things are preserved under this gluing construction, but many things are preserved in almost all cases. So how do we formalize this almost all thing? Well, it turns out that the result of this gluing only depends on one parameter, which is called slope. Let me denote it by sigma. So the slope, you can think of it as, so first let's take the image of the boundary of this disk. So where is it on the picture? It's here. So that's, right. That's the boundary of the disk. Okay? So let's take the image of the boundary of this disk. And let's take its free homotopy class, which you can think of as an element of the fundamental group of what? Of the boundary you think of this as an element of the fundamental group, and it turns out that up to homeomorphism, the whole construction only depends on this parameter, which is called slope. So basically, this is where this curve goes in the boundary of this manifold. So you fix the slope, which is the curve, a free homotopy class of curves in the boundary of this manifold, and then you do this torus in such a way that this thing goes there, and that's it. So, by the way, it's useful to understand what is the fundamental group of the resulting manifold. So what is the fundamental group of n of sigma? Well, of course, when you glue this solid torus so that this disk gets glued to sigma, you kill sigma, right? So the fundamental group must be the quotient group of the original, of the fundamental group of the original manifold, and modulo the normal closure of the slope. Right? So you kill this, so you have to take quotient, and then it's an easy consequence of the Seifert van Kappen theorem that nothing else gets killed. Right? So basically it's Seifert van Kappen. So now here's one example of a theorem which says that some nice properties of the resulting manifold n sigma can be derived from nice properties of the original manifold n. So the theorem was proved by Thurston, and that's called hyperbolic dam surgery theorem. So suppose that n has a complete finite volume hyperbolic metric. Then for all but finitely many sigma in pi 1 of n, the resulting manifold n of sigma is hyperbolic. So for example, if you take any hyperbolic knot complement, say take three-dimensional sphere, embed a figure 8 knot there, I guess everybody knows what figure 8 knot is. So you embed a figure 8 knot there, it's a hyperbolic knot, so if you drill along this knot, what you get is the so-called hyperbolic knot complement, which is complete finite volume hyperbolic manifold. And then for all but finitely many gluings, for all but finitely many slopes, the resulting manifold is a closed hyperbolic manifold, right? So you can restate it in terms of fundamental groups. So the corollary of this theorem is that for all, well, under the assumptions of this theorem, for the same n, for all but finitely many sigma in pi 1, why is it pi 1 of n? It's pi 1 of the boundary, right? Sigma is the slope of the boundary, not the main. Well, it's so in general, of course, if you have a manifold with boundary, pi 1 of the boundary is not embedded in the pi 1 of the manifold, right? Embedding of submanifolds are not necessarily pi 1 injected. But this is always the case under the assumptions of this theorem. So if you have a hyperbolic, complete finite volume hyperbolic manifold with storic boundary, pi 1 of the boundary is always embedded into pi 1 of the whole manifold. So for every sigma in pi 1 of the boundary of n, that's actually why I can take this quotient group, because in general I should be a little bit more careful. So pi 1 of, for every sigma, for all but finitely many sigmas, the fundamental group of n of sigma is hyperbolic. So historically, this was the first evidence towards, the first non-trivial evidence towards the geometrization conjecture, because what it actually says, it says that for all but finitely many fielings, the resulting manifold is already geometric, so there is no need to decompose it. It's already geometric, has geometric structure, which is of hyperbolic type. So now, of course, we know that geometrization conjecture is true, but still the theorem is very interesting. What I'm going to talk about is an algebraic analog of this theorem, so you can kind of generalize it in terms of groups. Well, it's not obvious that this is a generalization. It will be obviously a generalization of this algebraic statement, but modulo the geometrization conjecture, it will also be a generalization of the geometric statement. But interestingly, that this purely algebraic result, which is the analog of the Thurston theorem, was used in many places, including three-dimensional geometry. So, for example, it was used by Abel in his solution of the virtual Huygens conjecture, and it's also very useful in group theory. So, my goal will be just to explain the basic statement of the analog of the Thurston theorem in group theoretic settings. So, let me first draw a little table which tells you how to translate terms from three manifolds to group theoretic language. So in case of three manifolds, we have, well, here we have groups, and here we have the phi1 functor. So in case of three manifolds, we have several things we have to translate. First of all, it's a complete finite volume hyperbolic manifold, it's called N. Second thing we have to translate is the boundary of N. And then we have to understand what is a slope in case of groups. So remember, sigma was phi1, was an element of phi1 of the boundary of N. So in case of groups, complete finite volume hyperbolic manifolds will be replaced with acylindrical hyperbolic groups. The boundary will be replaced with a hyperbolically embedded subgroup, and I'll explain what it means. And slopes will be replaced with elements of this hyperbolically embedded subgroup. So, or even more generally, if you think of this slope as the cyclic subgroup generated by sigma, which is a subgroup, a normal subgroup of phi1 of the boundary, phi1 of the boundary is z plus z, so every subgroup is normal. You can more generally replace this with normal subgroups of H. This is kind of more general situation. So this is the way to generalize, well, to translate whole theory to theoretic language. Now let me explain what hyperbolically embedded subgroups are. So you already know what these hyperbolic groups are. Now what about hyperbolically embedded subgroups? Well, let me start with a general definition. So this is a notion which was introduced in my paper with Francois Demani and Sam Girardel. Let's fix subgroup G, let's fix a subset of G, and let's fix a subgroup of G. There are no assumptions whatsoever. Just G is a group, H is a subgroup. We don't assume X is finite, we don't assume X generates G. The only thing which I assume is that G is generated by X together with H. So in this case I call X a relative generating set of G modulo H. So I can consider the Kerr graph gamma of G with respect to X union H. Every element of H is inside a set of generators, so even if X was finite, this relative Kelly graph is normally not locally finite because H may be infinite. And inside this graph, I consider the subgraph gamma of H, comma H. Let's call it gamma sub H, and this is gamma sub G. So this is a complete graph on cardinality of H many vertices, right, which sits here. So here is the picture. This is my big graph gamma sub G, and here I have this complete graph gamma sub H, something. Okay? So now we say that H is hyperbolically embedded in G with respect to X, and my notation for this is this. So I use this subscript H to stress that it's hyperbolically embedded if the following two conditions hold. So this notion is supposed to generalize the notion of a relatively hyperbolic group. So it's almost like G is hyperbolic relative to H. There will be a precise relation between this notion and relative hyperbolicity. I'll mention it later. So if, as in the case of relatively hyperbolic groups, you first require that the relative Kelly graph gamma sub G is hyperbolic. And second condition, to define the second condition, I need some, well, one more technical definition. So let's denote by delta the graph which is obtained from gamma sub G by excluding all edges but not vertices of gamma sub H. So delta is everything here, plus all vertices here. Okay? Maybe it's a disconnected graph, I don't care. It's not necessarily connected. To some graph, I exclude all vertices of this particular copy of gamma sub H. I don't exclude, so there are, of course, copies of gamma sub H which correspond to cosets, right? I don't exclude those. Just edges of this particular thing. Now, for any two elements, G and H, in gamma sub H, well, in H, which I think is the vertex set of gamma sub H, vertex set sub H. For any two elements, we define the distance, let's call it d sub H, between G and H, to be the length of a minimal, which means shortest path between G and H in delta. Well, infinity, if such a path does not exist. So such a path may or may not exist. Of course, in the original graph, gamma sub G, the distance between two vertices is just 1 because there is an edge. Remember that we include all generators of H into the generating set for this graph, right? So there is just a straight edge from here to here. But now we excluded all these edges, so we cannot go straight. Now we are forced to go outside. So this is my delta. And then if there exists a path which avoids all edges of E sub gamma, E gamma A, well, of edges of gamma sub H, then the distance is just the length of such a minimal path, otherwise it's infinite. So the second condition is that for every natural number, there exists only finitely many elements of R of H such that elements H in H such that the distance in H between 1 and H is at most M, i.e. H equipped with the distance function d sub H. Now this is the so-called extended metric. It can take infinite values, but it's still a metric. It satisfies the triangle inequality and everything else, right? And of course you just extend all the algebraic operations to 0, infinity, including infinity in the natural way, like infinity plus infinity is infinity, and so on. So this is an extended metric, so this extended metric space is proper. Or locally finite if you want. Every ball of finite radius is finite. So this is the definition.
Gamma G is less than or equal to gamma H.
Yeah, it should be that way.
The other way around. Second line on the board.
Second line.
You call the new.
On the left.
The other way
The
around.
name is the other way.
Thank you. So let's consider two examples, just to understand this notion. So the first example, well, maybe more than two. So first is example number 0, which is kind of stupid example. Suppose, well, H is just G. So every group is hyperbolically embedded into itself. Why? Well, proof. Take X to be the empty set. X is empty. Now what do we have? So X union H in this case is G itself, right? So H equals G. So X union H is G itself. Gamma sub G becomes a graph of finite diameter, right? And delta does not have edges at all, right? So the distance between any two distinct points is infinity. Which means that the first condition is obviously satisfied because it's a set of bounded diameter. The second condition is satisfied because this distance is infinite unless H equals 1. So for every n, there is just one element which satisfies this inequality, the element. That's it. So similarly, if H is finite, then we always have that H is hyperbolically embedded in G. So for every finite H is hyperbolically embedded in G. And for the proof, we just take X equals G. So again, it's the same trick. You force gamma sub G to be hyperbolic by making it of finite diameter. So now again, gamma sub G has finite diameter 1. And so the first condition in the definition of a hyperbolically embedded subgroup is obviously true. Now how about the second condition? Well, it's obviously true as well because H is finite, so of course every ball of every radius in H is finite, right? This is kind of the generate examples. And all other examples are called, all other hyperbolically embedded subgroups are called non-degenerate. So non-degenerate means proper and infinite. Okay? So now let's talk about some non-degenerate examples. So the first example I want to consider is actually not an example, but it shows how the second condition can fail even if the first condition is true in that definition. So let's take G to be Z cross H, and suppose